All right, let's talk about something truly terrifying. A force of nature that often hits after the ground has already stopped shaking. We're talking about earthquake-induced landslides. And we're zeroing in on one of the most volatile places on the planet, the Indian subcontinent. You know, when we think of an earthquake, we picture the ground trembling, buildings swaying, that raw, incredible power. And yeah, that's absolutely terrifying. But in a place as massive and as steep as the Himalayas, that initial shock, it's often just the opening act. The real lasting devastation, the thing that changes the landscape forever, often comes moments later. It's the sound of entire mountainsides rattled loose by the seismic waves finally giving way. Today, we're digging into what happens when the shaking stops and the sliding begins. So how exactly does this happen? How does a tremor deep in the Earth's crust translate into a whole mountain on the move? To get that, we need to understand the destructive partnership between these two powerful geological forces. First things first, what exactly is a landslide? Well, at its most basic, it's just a mass of rock, soil, or debris moving down a slope. Sometimes it's a slow creep. Other times, it's a terrifyingly fast avalanche. But every single time, it's about one thing: gravity winning the battle against a weakened hillside. Now, you've probably heard about landslides caused by, say, heavy monsoons, right? Where so much rain falls that the ground basically turns to liquid mud. That's one kind. But what we're focused on today is a whole different beast. Landslides triggered by the sudden, violent jolt of an earthquake, a force that can literally fracture solid rock. So why here? Why is this specific region so incredibly prone to these disasters? What are the unstable ingredients that make the Himalayas such a geological hotspot? Well, the answer starts deep, deep beneath the surface. It all begins with the very ground we stand on. See, the Earth's crust isn't one solid piece. It's more like a giant jigsaw puzzle made of massive tectonic plates, and they're always on the move. An earthquake is just the spectacular release of energy when these plates grind against each other. And right here, we have a front row seat to one of the most dramatic collisions happening on the planet. The Indian plate is relentlessly shoving its way north, crashing into the Eurasian plate. This epic, slow-motion crash is what created the Himalayas in the first place, and it's still building up mind-boggling amounts of pressure, making the whole region a seismic minefield. Okay, here's where the physics gets really interesting. Scientists measure the intensity of the shaking using something called peak ground acceleration, or PGA. And what they've found is a critical tipping point. Once the shaking gets stronger than just 0.05 G, that's only 5% of the force of gravity, it's often enough to overcome the friction holding a hillside together. It's the final push. Think of it like a chain reaction, a series of dominoes. First, the plates collide, building up pressure for years, sometimes centuries. Then, boom, an earthquake releases all that stored energy in a matter of seconds. And finally, that intense shaking is the trigger that causes already vulnerable steep slopes to fail. It's a direct line from tectonic pressure to catastrophe. And this isn't just a theory, you know. This region has a recent, tragic history of these events. So let's look at 5 specific earthquakes, because each one tells a very different story of destruction. Over just the last couple of decades, the region has been rocked by at least 5 major quakes that triggered major landslides. And you can see they vary a lot in magnitude, from the absolutely massive 7.6 in Kashmir and 7.8 in Gorkha to the more moderate but still really destructive events in Sikkim, Uttarakhand, and Assam. What's really crucial here is that not all these events play out the same way. Just look at the data. You can see a clear link between the quake's magnitude, its shaking intensity, that PGA value, and the kind of landslide it creates. The Gorkha quake, a monster 7.8, unleashed enormous rock avalanches. Now compare that to the much smaller 5.1 Uttarakhand quake, which caused more localized slides. The power of the quake literally shapes the disaster that follows. And to get your head around the sheer scale we're talking about, just look at this quote. It's about a single landslide from that 2005 Kashmir quake. The Hathianbala landslide moved over 100 million cubic meters of rock and debris. I mean, that's an almost unimaginable volume of stuff, more than enough to bury entire towns and dam up rivers, which is exactly what it did. And it's not just about how big these are, but also what they're made of. In the super steep high Himalayas during the Gorkha quake, you got these massive rock avalanches that could travel for miles. But in Assam, the geology is different. The quake there triggered shallower slides made of soil and loose rock. They were still destructive, for sure, but much more localized. The ground itself really dictates the kind of disaster you're going to get. Okay, so understanding the problem is one thing, but the real goal is to save lives. So what can actually be done about it? This is where we get into the science and technology of trying to outsmart these disasters. Scientists and engineers have developed a pretty powerful toolkit. It all starts with looking at the past, creating detailed inventories of old landslides to spot patterns. Then you use that data to map out the future danger zones. This info feeds into early warning systems, lets us use satellites for real-time monitoring, and, crucially, helps develop better, smarter rules for where and how we build things in these high-risk areas. The whole point of all this work is to make a really fundamental shift in thinking. Instead of just reacting after a disaster, sending in rescue crews to sort through the rubble, the goal is to use science to get ahead of the problem, to prevent the worst outcomes before the ground even starts to shake. The tectonic plates are never going to stop their slow, powerful dance. The mountains they've built will always be fighting against gravity. The ground beneath us is fundamentally and always will be unstable. So the real question is, can our science, our planning, and our preparation move fast enough to stay ahead of the next inevitable shift? Thanks for joining us on The Explainer.